Let's talk astronomy though. The giant Magellan telescope's final mirror fabrication begins. This sounds like a very, very boring astronomy topic. And to be honest, when I saw the headline, I kind of thought it was going to be pretty boring. But then I actually started reading and learning about A, how this process is done, and B, what the telescope is actually capable of. I knew it existed, but I didn't really know what it was. I didn't really know much about it. It's really cool. So let's talk about it. This is a neat little image of all of the glass being set for the final mirror of the 7-mirror giant Magellan telescope that is being constructed and placed in Chile. The important thing to note is that this is the size of one of 7 mirrors. Notice how big this is. This is real. Like, this is a real thing that is being constructed. Look at how big it is compared to these guys. It's gigantic. But if you look at this thing that this guy is holding, this entire thing is full of them. And what these are cubes of what's called borosilicate. It's a certain type of glass that's used for making optics, which ironically enough is something that I'm rather familiar with. And they are putting this glass all throughout this big mold that's going to turn into the final mirror. You might ask, well, what's the point of doing that? Well, let's actually take a look at what the point of doing that is. This is what the telescope's going to look like when it's all complete, and we'll learn a little bit more about that later. But I do want to talk about these sizes. So each of these individual mirrors, these are the portions of what are called the primary mirrors. They are 8.4 meters in diameter. That is a 2-scale giraffe. Just to be clear. And when we have the entire thing across, it's about 25.4 meters, and it is an entire whale across. This thing is huge. Absolutely gigantic. One of the biggest ground-based telescopes we've ever constructed. What this thing does, or what they are doing, I should say, what these people are doing is they are placing some of the purest glass that we are capable of producing into this giant oven. That's what this thing is. It's a giant oven. So they're putting it inside this giant oven by hands to make sure it covers as much space as possible. And they're going to close it, and then they're going to spin it while the glass melts. Now, inside of here, this goes to, I believe it's like 1300 degrees Fahrenheit, if I remember correctly. And the entire thing spins as it's doing this in order to cause all of that liquid, all of that viscous fluid to start to go into a paraboloid shape. When you spin water in a container like this or any fluid, it forms this shape, a parabola, which is something that most people know from like high school math courses, right? And it's like, well, what am I ever going to use a parabola for? It turns out if you have light shining on a parabolic surface, it focuses all of that light to a single point. And that's a super useful thing when you're trying to measure astronomical objects. It's very helpful. So we use parabolic mirrors all the time. And if you do it in a 3-dimensional thing like this, you form a 3-dimensional parabola, a parabolic surface. Once you have that parabolic surface, it's not perfect, because this process right here, it will, in theory, make a perfect parabola. If you had a perfect fluid that didn't interact in any way, it wasn't viscous, you didn't have any weird anomalies in the actual spinning, gravity was totally uniform, which is a pretty good assumption for most cases, none of this ever works out perfectly. So what we end up getting is we end up getting something that is close to a parabola, but you still need to actually fix it, more or less. This happens in optics all the time. We'll make, spherical optics. I actually have a few optics up here. We'd make like this. This isn't a parabola. Actually, it might be a parabola. It might actually be a hyperbola. I'm not sure. This is an A-sphere, is what we would call it in the optics business. And this type of thing will get surface formed first, but then you have to take it into another machine to really cut it down to the exact parameters you want it to be. So you'll get it close, but you need to be within, for this particular optic, this is a reject, so it probably wasn't good enough. But if it wasn't a reject, if this was a real science piece or a real industry piece, you'd be getting down to on the order of like 1/100th of the width of a human hair. This telescope actually needs to be on the order of 1/1000th of a human hair. And it's also worth noting, keep in mind, we're going to 1/1000th the width of a human hair over a surface that is gigantic. So we have to do this process of polishing all over the surface. And that surface is freaking huge. And there's 7 of the things. Turns out that with all of this involved, this is a 4-year process in order to make one of these mirrors. At the moment, 3 of them are done. Another 3 of them are in production, and we just started on the 7th. Theoretically, this telescope can run with only, I believe it's 3 of the mirrors other than the center one, and the center one is done. So once we get the 4th one done, we should be able to actually put the telescope online and start getting some test images to make sure everything else works. But we still won't be at its maximum capacity until we actually get this mirror done, which is about 4 years in the future because it just started. Now, I also want to talk about the telescope in general because it's just a very neat science instrument. I will warn you, if anybody here has like epilepsy or something, this page likes to flash a lot. So be aware of that. This flash warning right now. So this is their, yep, see, there it goes. This is their page for the actual telescope. You can get all of the information here. Literally everything from the enclosure out to the mount, if you want to learn about the mount, to the primary mirrors like we were just talking about. But the thing that I want to talk about a little bit right now is this, adaptive secondary mirrors. This raises a very interesting question right at the front, one that people don't tend to know the answer to. Why do stars twinkle? Well, it turns out the stars aren't twinkling. Stars really shouldn't be changing their brightness that much unless they're variable stars. They should be pretty consistent. The reason a star twinkles is because of the atmosphere. So as air currents and different temperatures and different variations in sort of the air pressure in different spots, as all of those different things start to change, you can get variations in the light that comes to us. Effectively, any medium that light will travel through, if it is changing or it's not uniform, will cause the light to bend in weird ways. And that can cause optics, even as big and good as these optics, to not give us the best image on the ground, which is why we send a lot of things into space. This is way too big to send into space, so we need a different way to solve this problem. And what we do is we use what are called adaptive optics. Adaptive optics are nuts. Effectively, what they are they're optics, or mirrors in this case, that are on pneumatic actuators. And a lot of the time what we'll actually have is individual pieces of these mirrors will be able to move individually, or you can have a big set of pneumatic tubes behind it that can push or prod different parts of the mirror to deform it ever so slightly. And when you do that, you can effectively deform the mirrors to subtract the deformation from the atmosphere. Let's say it's causing a big circular image to like get squished in this direction, right? We can force the mirrors to make that image then unsquish in the same direction it was squished. We basically just undo whatever the atmosphere does in real time, which is crazy. This type of thing has been theorized forever. I believe the Keck Observatory was the first one to ever actually implement it, and the results are stunning. Now, of course, that requires us to have a perfect model of what the atmosphere is doing to our light. You might have noticed in the beginning of all of this, if I scroll all the way back to the top, that these images of the observatory show these big yellow lines, and you've probably seen these before. For example, this one. You might not have known what these are. They are called guide lasers, and they're these very strong sodium, usually lasers, that are pointed into the sky to make a fake stellar source. Effectively, we point them up, we point the telescope to where they're shining in the sky, and we let the telescope figure out, using that guide star's light, what the atmosphere looks like between us and space. And with that, the computer can then figure out how they need to deform the mirrors, which will then allow us to see the things beyond the atmosphere with clarity. So we effectively make a fake star and say, hey, how would we have to change this to get it to be what we know it should be, and then use that on everything else, which is wild. It's a really, really cool concept, and it's very, very hard and resource intensive. So this is some of the really cool parts about the giant Magellan telescope, which is not the only Magellan telescope, if you were curious. If you want to learn more about this, their website is fantastic. They also have this giant science book for those that are a little more scientifically literate, talking about all of the different things that this thing can do and what it's supposed to look at. This telescope is going to look at basically everything of import in terms of really any astronomy we could ask. One of the big things, it's going to be one of the only, if not the only, telescope that we can actually see exoplanets on, and it'll help us with the search for exoplanets. We can look at the births of stars if we look far enough back. We can look into supernovae and their depth of stars. We can look at the Milky Way and the galaxies around us. We can look at galaxies in the very ancient past, etc., etc., etc. This thing is a huge thing. This is a very, very cool project, a very, very neat telescope, and one that I really didn't know a lot about until today, so hopefully you found it as interesting as I did, because this stuff is really nuts.